We're going to change gears again, and we're going to start talking about oxidative addition and reductive elimination. Different type of a reaction. We're going to be interested in adding a pair of bonds or a pair of ligands across the metal center. This is oxidative addition of two new ligands. This direction is reductive. You're reducing the metal center from Q+2 back to Q. These metals are usually less than or equal to 16 electrons, and you have to have some d electrons there to do this kind of chemistry, because when you oxidize the metal, you're giving up 2d electrons and making bonds. When you do oxidative addition, you're actually contributing electrons to the valence shell of the metal. Okay, so you can't be higher than 16 or else this doesn't work. And you have to have more than 2d electrons. So it's pretty classic for square planar D8 compounds or D10. And XY is often hydrogen or sometimes a CH bond, often XH bonds or RX bonds, where X is halide or halogens. So we're going to do some mechanisms of this reaction. First one we're going to do is protonation and alkylation. These are really SN2-like mechanisms, where the metal is doing the SN2 on the substrate. Let's start off with iron pentacarbonyl reacting with H+. Over here, we've got 8, we've got 10. This is 18 electrons, iron 0, D8. And on the right here, we have added no electrons to the valence shell. So this is still 18 electrons. Now it's iron 2, D6. And that's because 2 of those electrons ended up in the iron hydride bond, and we say metal plus ligand minus. We're going to do this one again in a few minutes. But I'll just leave it like that for now. There's a lot of radical chemistry in oxidative addition, many of which were studied by Halpern. Back in 1970. We're going to start with this cobalt 2. This is a 3- compound. And it reacts with alkyl halides. And interestingly, the way it does it is it rips off the halide. And it spits out an R dot. So why does it work that way? Well, this guy, we've got, the way that I'm going to count this, I see that this compound is 3-. And so I'm going to call 3 of these cyanides cyanide anions that donate 2 electrons. And the other 2 cyanides, I'm going to say are X-type interactions that donate 1. So that's how I handle the 3- charge. You could also say 1, 1, 1, 1, 1 plus 3 to get 5, 8, and 9 for cobalt. So this is cobalt 2, D7, 17 electrons. You rip off the halogen, now you're at cobalt 1, 2, 3, which is D6 and 18 electrons. The halogen electron contributes 1 more to the valence shell. So interestingly, we oxidized the metal, but the valence shell count went up. Now this compound over here on the left, we've got x squared minus y squared. That's the one in the plane with the 4 cyanides around it. We've got z squared. That's also sigma star. It's lower than the x squared minus y squared because it's missing one of its ligands. And then you've got xz and yz. These guys are pi, and you got an xy, that's pi. Cyanides are pi acceptors. So let's put in our electrons. Cyanide's a strong field ligand, so this guy's going to be low spin. So you can see you've got 1 electron in that z squared orbital, right? The z squared orbital occupies the space above that square plane, right where I've drawn that lobe with the dot in it. So this free radical has all of its unpaired spin in the empty space there. Now this R dot that you make, what is it going to do? Do a lot of things. It could go rip a hydrogen off of something. It can go find another R dot. But 2 radicals reacting with each other can be very fast if you have a high concentration of them. Generally, you don't have a high concentration of free radicals, especially in a radical chain type of a mechanism. But in this case, cobalt 2 is a free radical. R dot is a free radical. So these 2 guys get together. And now you have a new cobalt 3 reacting with a new cobalt 3 product with the metal R bond. So reaction with cobalt 2 is faster than 2 R dots reacting with each other because the R dot is very short-lived, and therefore you're never going to build them up in concentration enough. Those of you writing reaction mechanisms for like photochemically driven processes, you're going to want to draw a lot of free radicals after charge transfer. Those compounds don't tend to build up in concentration. So you should be very careful about drawing two of them getting together to do some forward reaction with any kind of a reasonable rate. Okay. So let's take a look a little bit here. This reaction has second order kinetics. The rate is equal to some K times the concentration of cobalt-2 pentacyanide, 3 minus, times the concentration of Rx. Okay, so that says that the rate determining step involves 1 cobalt-2 and 1 Rx. There are 2 cobalt-2s involved in the overall transformation. This one and this one. But the rate equation only considers one of them, and that's because this is the slow part. Once you make the R dot, this reaction happens so much faster, it doesn't impact the kinetics at all. So the hard part is making the R dot. Once you make the R dot, it's over. So the rate of the reaction is only dependent upon this process here, not so much on that one. So this K was measured for a series of different Rx's, including methyl iodide, ethyl iodide, isopropyl iodide, and terbutyl. And you see the rate goes up. Why does that happen? What's happening as we go this way?
Increasing the sterics.
You're increasing the sterics by a lot. Terbutyl is much bigger than methyl. Now, if you ask, why does that correlate with the rate improving? So the rate is increasing by a factor of 100 on increasing the sterics of the alkyl iodide. Does that make sense?
So stabilizing the radical.
That's the other answer to this trend here. Remember, now, Halpern didn't know the mechanism before he started this, okay? He just knows that if he takes cobalt-2 and an alkyl halide, he gets a cobalt-3 halide and a cobalt-3 alkyl. So he says, well, there are a variety of mechanisms you could write. How do we figure them out? Well, he looks at the concentration dependence of the alkyl halide, and he says it really only depends upon cobalt in a first order way and the alkyl halide in a first order way. But we see this trend where when we increase the sterics, the rate gets faster. And then some smart student says, but you've also stabilized the R dot because a T-butyl radical is quite a bit more stable than a methyl radical. That's why the rate gets faster. And so that is the evidence for this mechanism up here, right? This trend in the kinetics of the reaction supports the formation of the R dot here. Because when the R dot is a tert-butyl dot, it should be faster. And it is. So I'm going to say weaker CI bond, but the other way to say that is more stable. So those terbutyl iodide should be far less reactive if it were some SN2 type of an iodide displacement reaction. And instead, sterics don't matter. Okay. You can think about olefin binding and oxygen binding as a type of oxidative addition. So,
Professor, I'm sorry,
yeah.
can I clarify a question I have then?
Yeah.
So the sterics don't matter, but it is the sterics that are stabilizing the radical? Is that what you're saying?
Yeah, I think I get that. I mean, I think it's not, I wouldn't say that the sterics stabilize the radical. Okay, so when you have a tert-butyl radical, what you get is pi interactions between the adjacent CH bonds. Okay, so these adjacent CH bonds make a pi interaction with the radical that sits in the p orbital of the tert-butyl dot. And that makes that radical much more stable. So the reason it's faster is not steric. It's really about stabilization of the product. The sterics would say something about how crowding impacts the kinetics, but crowding doesn't impact the kinetics. Plucking off the iodine is really about stabilizing the R dot.
Okay, thank you.
Okay, so Vasquez complex. Well, this is not Vasquez complex. Oh yeah, it is Vasquez complex. Well, I forget if the phenyl is or if it's the ethyl. Reacts with O2 in this way. Makes this oxetane. The bond distance here is 1.44 angstroms, which is that of a single bond. O2 has a DOO of 1.21 angstroms. So it's quite a bit longer. So this thing here is like O2 2 minus, or an A to 2 peroxide. And that takes this compound here, which is going to be D8, 16 electrons square planar, to D6, 18 electrons octahedral. That's an oxidative addition. You know, olefin complexes as you know, they have these metallocyclopropane resonance forms. So you can draw this thing as iridium 1 or iridium 3. Just resonance structures. But the length of that OO bond suggests that when O2 binds in this fashion, it's really oxidative. Okay, I think I'm going to stop there. Don't want to get into that next part because it's a long road. All right. Some of you have noticed, I'm sure, but our final exam is scheduled for Tuesday the 20th. And I'm going to just stick to that date. And we're going to hand out the final exam, and you're going to have 24 hours to turn it back in. Okay, just like last time. Same format as last time. It's going to be a comprehensive exam. And, you know, you're definitely going to be making molecular orbital diagrams. You're going to do some group theory to assign vibrational stretching frequency information. You're going to need to know periodic trends. You have to know the periodic table. You're going to do lots of electron counting and symmetry problems. A lot like what you're seeing on your homeworks, okay? There's going to be some organometallic chemistry reactivity that's going to be a little bit freeform. And you're just going to have to try and figure that stuff out. You're not supposed to collaborate with anybody on this, and you should not search for answers on the internet. And yeah, other than that, it's basically the same as before. I would like to do a review session for the exam, and I unfortunately have a appointment on the 20th, and really also on the 19th. I, in principle, can do one on the evening of the 19th. So that's my current plan, is to do one on basically nighttime on the 19th. And I think probably the best thing to do is to follow through over email. But for right now, if anybody out there knows that there's a big problem with the evening of the 19th, it would be helpful to get an email from you saying so. And if there are a lot of people who all agree, then we may do something on the weekend beforehand. So like last time, that review session is going to be about me answering your questions. And so you guys need to come to me with things that you want to hear about, things you want clarification on it, and so forth. So,
Hi, Professor Owen. I just have
yes.
a quick question.
Yeah.
I know, like, I was looking at the quote unquote exam calendar, and yeah, obviously our exam is scheduled for the 20th. I think it was scheduled for the morning or whatever. Are you just planning on having it, like, the exam be given out at class time and then 24 hours from class time? Or is it going to be like, if it's scheduled for 9 a.m., then it's going to be given out at 9 a.m. on the 20th and then be due at 9 a.m. on the 21st?
I hadn't really thought about the time carefully. Probably it'll appear around lunch. Is there a reason you would like it one way or another?
I know some of us have like different finals the next day and stuff, so I just was trying to plan accordingly. No worries, like I don't think it necessarily matters for me specifically. I was just curious.
Okay. Yeah, I think I'll probably aim for noon that day. Okay. Anyone else? All right. Well, if not, I will see you on Wednesday. recording here. So I noticed some errors on the last problem set that I didn't when I looked at it before, and I wanted to talk through some of them. I think as a result, I want to delay the due date for today's homework set till tomorrow. I just want to make sure, I really want to make sure you guys know how to count electrons properly. So I want to go through some of the examples just to make sure we're on the same page. And I'll give you another 24 hours to edit your current problem set. So let me just share my screen here. All right, so before we start doing lecture 24, I wanted to make note of a couple of things. So electron counting and N-heterocyclic carbene. So N-heterocyclic carbenes, they're confusing. The community has adopted a strange way of talking about them, okay? N-heterocyclic carbenes are these Fischer-carbene ligands that are made by taking an imidazolium salt, typically, but not always. This salt is deprotonated. And you get this charge neutral product. People often write this structure. But it's a terrible structure because this implies a hydrogen is here. But in fact, it's not. Okay, it's this thing. So these imidazole rings with the that have been imidazoliums that have been deprotonated to produce a charge neutral carbon donor ligand. These N-heterocyclic carbenes, they are L-type ligands. Okay. Not explicit. Problem 4. We didn't really define that for you. I've forgotten whether we talked about that formalism in class or not, but that drawing, it's bad. It violates the principles of drawing organic compounds, and yet it's commonplace. So you have to know that. You're going to see structures like that. Be aware this is an oversight the community has adopted. All right. Another one is the tantalum problem. So there's this tantalum thing. And I'm going to write it like this for the time being. I'll finish the structure later. But this thing over here is problematic because these two nitrogens, as drawn, if you were to draw a closed shell fragment, it would be 2- for each nitrogen. That's not the real structure. We got we got our wires crossed here, and there should be something else on this nitrogen. Okay. So there's a problem with this structure. This structure would be open shell with radicals on nitrogen or something like that, as drawn in the homework. So compound 5 is wrong, and the answer in the answer key is wrong. If this thing were like this, now you could imagine, say, 2 negatively charged nitrogens, 2 hydrides, and this would give you tantalum 4. Okay, so really this structure should have been tantalum, tantalum, it should have looked like that. Right, so this is tantalum 4. You got 2 hydrides donating their tantalum hydride bonds to the other tantalum, so that gives you a total of 4 electrons being added to the valence shell of each tantalum center by these L-type interactions. And when you have tantalum 4, you have 1 d electron. That means you can have a metal-metal bond. Sometimes people draw a metal-metal bond and there isn't one. So you have to think about the number of d electrons available to make a metal-metal bond, and then decide for yourself whether a metal-metal bond makes sense. And it does in this case if the nitrogen has an R group on it. Okay. One more. Let's do this. Let's do the, well, we're going to do compound 6 today. So we'll come back to that. I want to take a look at, where did it go? It's compound 12. So compound 12 is this niobium complex. This guy. So I'm going to just do a little bit of math here for you for a second. I'm going to pull this thing apart by pulling off a tetraphenyl borate. This compound over here on the right has a negative charge. That little piece. It's kind of like BH4 minus or BF4 minus. You got 4 anionic things around that boron to get you to a 1 minus charge overall for the boron. So borohydride, tetrafluoroborate, anytime you see 4 bonds to boron, you should be thinking anion, unless something really wacky is happening or it's bridging. in some way. You got to think about that formal charge out there. So tetraphenyl borate is a common anion that coordination chemists use. It's nice and stable and big and organic. So when you pull off tetraphenyl borate, you got to leave behind a positively charged niobium. So like sometimes your ligands can have a negative charge associated with them. There could be a negative charge out on that boron, and you have to neutralize that negative charge to arrive at a neutral compound overall. Okay, anybody want to ask a question about that? We'll do another example.
Hi, yeah, sorry. Can I ask a question about that?
Absolutely.
It's tangentially related, but it's just about like the dative bonds
Mhm.
to boron. So I guess I just have a hard time like wrapping around my mind around when we have like a cationic metal center, still electrons being able to be donated into that dative bond. And so this is kind of related to that because you're like pulling the boron away and giving a positive charge to the niobium. But you don't pull the boron away when it's a dative bond and give like another negative charge to the iridium or whatever metal center it is, right? Or do you?
Well, so what's not drawn here are formal charges. The compound on the left does not illustrate that there's a formal negative charge on the niobium center. And so you have to be aware of that when counting charges on the metal. There are a variety of other ligands that have that feature too. You know, even N-heterocyclic carbene. So if you have a metal, if it were drawn like this, you know, one way to count this would be to say plus, and if this whole thing is neutral, you got to have a minus out there.
Okay. Yeah.
Okay. So,
Yeah.
so you have to be aware, sometimes there are formal charges out on the ligands, and you must achieve a charge neutral thing overall, in which case you need to write that formal charge in the metal. Now, another way to draw this is just like this. Right, and so here, this fragment is charge neutral on the right, and the metal doesn't have to balance the charge when it's drawn in that way.
Yeah. But so I guess like so with the boron dative bonds, obviously like the arrow is going the other way, right? From the metal to the boron. And
Oh,
so
you're talking
in
about
that,
this type of an arrangement.
yes.
Okay.
I guess my question is, so you drew there, right? Like when the NHC is donating into the metal center, technically, you know, formally after the metal would have a minus charge, right? And then you would count that against the oxidation state, you know, like when you're determining the oxidation state of the metal.
Yeah, because this is really an X-type interaction in that resonance form.
Right. And so I guess my question is in terms of like the M boron bond,
Yes.
if you're donating into there, then technically that species that you have drawn, the boron has a negative charge and the metal has a positive charge.
Correct.
Is that positive charge, do you take that into account when you're counting the oxidation state of the metal center?
Yeah, so this is a tricky case. for that exact reason. Do you say that this bond raises the oxidation state of the metal or not? In this
Right.
resonance depiction, it does.
Okay.
Because we default say it's metal plus and ligand minus.
Mhm.
And then,
Okay.
there's also the version where you have an electron pair donating to an empty orbital. And in this case, it's the metal is acting as an L-type ligand and owns the electron still. So that would be a case where the oxidation state doesn't go up.
All right. So it is specific to the way that you've drawn it.
Specific to the resonance structure. Remember that, like with a carbene, particularly the Fischer carbines, you can also draw this. Now you have an X2 ligand.
Right.
So there's a difference between the oxidation state of this complex and this complex because the resonance structure is different.
Okay. That's also helpful for the homework.
Yeah.
Thank you so much. I appreciate it.
It's, I like to give you guys a challenge and make you think through this stuff, but you shouldn't be confused as to what the rules are. So, all right. Anybody want to ask anything else about this? I'm going to just do one more example. We talked about these TP ligands. I did that wrong. Sorry. That's what I wanted to do. Okay, so this thing right here is an anion. It has 4 of these paraziolate anions around 1 boron 3+. All right? You got to boil it down to the neutral fragment. The neutral fragment is this guy. Pyrazole. So you have 4 pyrazolate ligands around 1 boron. That gives you a borate, or tetrakiss pyrazolyl borate. People call it TP for short. Now, these 4 nitrogens can be neutral donors for a metal center. So is this an L4 ligand? Well, it doesn't bind with all 4 nitrogens. In fact, usually one of those pyrazolates is actually a hydride or a phenyl or something like that. But the point is that there's these neutral donors out there on the ligand periphery that can stick to the metal. And you arrive at metal complexes where you have I'll write an H out here, facially coordinating pyrazolate ligands with this boron out here, but the boron has a negative charge on it. And so you have to balance that with a positive charge on the metal if the complex is neutral. So beware of the negative charges out on the ligand. And it's sometimes nice to think about this as a L3 ligand with one negative charge. That's kind of a simple way to count it. It's sort of a pain in the butt to count this by the neutral ligand formalism. You know, you could call it XL2, but that's a little bit confusing. Okay, so beware the negative charges or charges in general out on the ligands. Okay, so satisfied?
Hey, I have a question.
Yeah,
So in the first example you gave with like the imidazole,
yeah,
you had it like binding to the carbon.
yeah.
If you have it binding to like the nitrogen, it's also like L type, right?
Yeah, so I'm not exactly sure I know which structure you're referring to.
Like number 4 on the problem set.
Compound, wait, which one? Problem set 5 or the previous? Or the
Like the
current?
one that we're doing right now. It's like the last question with like the like
Hey, Sarah.
with that like molecule.
Compound, which one? Which problem?
The very last question with the like axial imidazole ligands.
Ah, okay. Well, so those imidazole ligands are less complicated because you can pull off N-methyl imidazole as a neutral compound. So that's just a simple L-type donor.
Okay, that's what I thought.
All right. So, so we'll give you another 24 hours to get this thing in, which unfortunately means you're not going to get the answer key posted until Friday. Because if somebody's late, then I don't want to post the answer key. So it'll be available Friday afternoon. Review session on Monday evening. I will send a link, and other than that, let's move on here. Okay. Start over. Okay, so we're going to do some more oxidative addition chemistry today. We're going to talk about alkylation. Or protonation mechanisms. Remember, these are like SN2. And in particular, we're going to talk about oxidative addition of alkyl iodides. Let's revisit our Vasquez complex example. So iridium chloride reacts with methyl iodide in an SN2-like fashion, where you can make this kind of an intermediate. And so you've got two X-type ligands and a positive charge. That gets you to iridium 3. And this guy's then D6. It's not octahedral, so we're missing 2 electrons. This guy is going to be 16 electrons. it's very rapidly converted. This is a proposed intermediate, actually. So it finally gets down to the 18 electron product. Yeesh, I have a hard time with the pen today. Okay, so turns out the cis geometry is the thermodynamic product, but you actually end up making this trans compound. Okay, and there's some various thoughts about why that might be the case. It has a delta H double dagger. This reaction rate of, or the barrier height, is 6 kcals per mole. That's pretty small. That's a low barrier. Interestingly, the delta S double dagger here is minus 50 entropy units. Minus 50 entropy units is very negative. This strongly implies a associative or bimolecular rate determining step. Not surprising, but when the entropy is really negative, you take two things and you make one in the rate determining process. Okay. So this reaction turns out to be a little bit complicated. I think it's catalyzed by iodide, and so a lot of effort is put into it, and people have looked at it a couple of different ways. Jack Halpern looked at this reaction with a different approach. Rather than using Vasquez complex, he used this glyoxine complex, cobalt 1 DMG twice L plus, where DMG twice is equal to this guy. Eek. I'm just going to write the bonds in there. But the neutral compound would have hydroxyls on both nitrogens. And in fact, this thing has been deprotonated twice. And it makes this ring structure by forming a hydrogen bond to the adjacent glyoxine hydride or hydrogen. So maybe actually, I'm going to just edit this thing or put some more, be a little bit more thoughtful about this. So this makes a hydrogen bond in this way. Now, the left sides, you can't tell the difference between those OH bonds, but it's helpful to know that you have a formal negative charge out here and out here, giving rise to this 2- thing overall. So you have a 2- ligand, you have a +1 complex, and that gives you cobalt 1. So cobalt 1 DMG twice L plus reacts with Rx in the presence of L, and in the end you obtain this. And L here is PPH3. Okay, and what Halpern found was that the rate of this reaction he went through and he did his patented steric test. With a bunch of different alkyl bromides this time. Methyl ethyl isopropyl tert butyl, and he measured second order rate constant for this reaction. And he found it was fastest for the methyl, and it got progressively slower until there was no reaction. And so this says Steric's rule okay. So here, unlike the cobalt hexacyanide case, now we have a case that's clearly kind of an SN2 type of a mechanism, and it's faster for the sterically less encumbered substrate. So this kind of a thing actually proceeds with stereochemical inversion. And that was another thing that people were interested in. Well, you know, is it a radical or is it this SN2 type of a mechanism? And George Whitesides did a somewhat famous study back then where he made a substrate that he deuterated. And he reacted it with the FIP anion. The FIP anion displaces the X. And he wanted to know whether this reaction proceeded by inversion. So FIP here is this CP iron carbonyl anion. So we have 2, 2, 5, 8, and 1 electron. That's 18 electrons. It's iron 0, because you have 1 X-type CP ligand, and then that negative charge. You could say it's higher oxidation states than that if you want to push your electrons out onto the carbons to make double bonds. So what's up with this funky deuterated substrate? Well, the reason that Whitesides did this is that you can look at the coupling constants. To determine the stereochemistry. So this hydrogen-hydrogen coupling constant is small. So the hydrogen-hydrogen coupling constant along that ethylene group tells you about the relative position of the tert butyl and the X. So Whitesides found that when he applied, or when he reacted that thing with the FIP anion, he ended up with this isomer. Because FIP is kind of big and tert butyl's big. And it goes with inversion. SN2 chemistry inverts the stereochemistry of carbon, and it gives you this other isomer. And he said he found, or the student found, a large hydrogen-hydrogen coupling. there for SN2 with inversion. So, there was still a little bit of radical concern about radical chemistry in that study. Which So he went and did another study using a radical clock. And so what he did was he took FIP anion and he reacted it with this cool alkyl bromide, isopropyl methyl bromide, sorry, cyclopropyl methyl bromide. And in THF, in the presence of some bromide anion, he gets this product in greater than 97% yield. So why is that interesting? Well, if it's a radical, then you might expect FIP anion plus this guy to produce this product. This product undergoes fragmentation like this, and it produces this butynyl radical. So it ring opens, and it happens with a rate constant of 10 to the 8th per second. That's really fast. And that's at room temperature. So if you make that radical, it doesn't live for very long. It flops open. You end up with this butynyl radical, and you can go and test whether or not you find the butynyl FIP or whatever product. So the fact that it makes 97% says no radical chemistry in that conversion reaction. However, FIP anion plus this compound gives the desired, or I should say the product that's consistent with SN2 chemistry in 70% yield, and the ring opened product in 30% yield. So in the case of the iodine substrate, there's a little bit of electron transfer chemistry going on, perhaps. So it's possible that there are competing pathways here, okay? And that makes all this stuff tricky. So I think I'm gonna
Professor, sorry, just a quick question about the cobalt earlier. I think, is it actually like cobalt plus, or because like the DMG is, like if it's cobalt 1 and then the DMG is like 2 minus, then it should be like overall negative, right?
it's cobalt.
It's in the earlier complex, yes.
It's cobalt 1.
Yeah,
So,
but So should the overall charge be negative, not positive?
Oh,
Or
yes, this is wrong. Sorry, that's wrong. Thank you. Yeah, thank you very much, Yichun. Note here. Okay. All right, so I think that's enough. I'm going to stop with that and transition here to oxidative addition now. But we're going to talk about oxidative addition of dihydrogen. So here, things are a little bit simpler. There's no radical chemistry going on with dihydrogen. Okay, so you don't have to worry so much exactly about what the mechanism is. So in general, CH bonds are approximately 100 kcals per mole. Our X bonds are approximately 70 kcals per mole. So it's very different kind of bond breaking chemistry here. It's part of the reason why radicals chemistry is not important. Iridium adds dihydrogen this way, and it gives you the cis addition product. Unlike methyl iodide. So the reaction is second order. It has a delta H double dagger of 11 kcals per mole for the chloride isomer. And the delta S double dagger is minus 21 entropy units. Again, in support of an association of two molecules that's consistent with the second order mechanism. The rate is sensitive to the halide, okay? Iodide is greater than the bromide rate or the chloride rate. You get a factor of 100 difference in rate on going from iodide to chloride. Iodide is faster. And the simple explanation, of course, is that you're starting with iridium 1 with a single halide, and you're ending up at iridium 3 with two hydrides and a halide. So you're raising the oxidation state, and ligands that are electron releasing will stabilize iridium 3. That makes it more favorable when the iodide, when you have an electron-rich halide present. There's an isotope effect. What's an isotope effect? This is comparing the kinetics for H2 versus D2. And what they find is that there is a KHKD of 1.09. And what that means, hydrogen and deuterium have different bond energies for vibrational reasons that we're not going to get involved in. It's harder to break a D2 bond than it is to break an H2 bond. But they compare these two and they find essentially no difference in the rate. And this means that HH bond breaking is not the rate determining step. So how does that work? How do you have a second order reaction, two molecules coming together to cleave the hydrogen-hydrogen bond, and end up with a case where the bond strength doesn't matter? And the reason is that it's thought that binding is slow. So you have iridium 1, it adds dihydrogen, and you end up with what's called a dihydrogen complex that then undergoes hydrogen-hydrogen cleavage to go to iridium 3. And this is slow. This is fast. That's weird. I find that really weird. Why is that weird? Well, it basically says that this is a stable intermediate. You make it, you sort of fall into a well. And then it pops out of that well. It pops out of that well faster than you make it. Okay, but there's a distinct product with dihydrogen stuck. It doesn't just fall apart as soon as it approaches the metal. Okay, so the KHKD, the difference between the rate of D2 and H2 doing this, says that whatever it forms, there's very little bond breaking. You're not breaking the HH or D bond much. All right, so people have looked at the reverse reaction. The reverse reaction is called reductive elimination. And this guy, Bill Trogler, he took platinum chloride and reduced it using sodium naphthalenide and a hydrogen. You spit out some salt and you end up with this PME3 complex that has 2 hydride ligands. It undergoes interconversion with the transform pretty rapidly. And this cis form has some decomposition to platinum 0. And hydrogen gas. And this stuff goes on to platinum particles. And this tetrakis trimethylphosphine complex and he finds that this decomposition, which is not very clean because you have platinum metal precipitating, is first order decomposition. And it has an isotope effect of 0.2. What does this mean? So if he runs this reaction under D2 atmosphere and H2 atmosphere, the decomposition kinetics are different. It says that the KH reaction is slower than the KD. Okay, and this is because the PTH and PTD bonds are being broken in the rate determining step. That was Trogler's suggestion. But people said, you're making this metal stuff. This looks suspicious. So we need to think about this more. But Trogler's observation is basically correct. So then along comes Jack Halpern again. And Halpern did a different study. He took some platinum hydrochloride complexes and he reacted them with methyl lithium. Sorry, not methyl lithium. Methyl Grignard at -80 degrees C. And that would produce this platinum complex, square planar platinum complex, with a methyl and a hydrogen in the same molecule. And this compound was relatively stable. It's cleanly the cis isomer, but not isolable. So he could make this compound at low temperatures, but it wasn't really something he could put into a bottle. He did get a clean cis product. He didn't have this problem where there's cis and trans interconverting and all of that stuff. And if he warms it up to -25, he could get formation of L2PT0 and CH3H methane. And this guy goes on to make platinum 0 particles and L4 platinum 0 again. So what he did instead, actually, was he added another trick. where he added acetylene to this reaction, or diphenylacetylene. And in the end, he could isolate this guy cleanly. So instead of, he could avoid this platinum zero formation, making this metal particle and powders in his sample, and he could get this clean product. So Halpern came up with a better experimental system. It eliminated the cis-trans problem that was in Trogller's reaction, and he produced a homogeneous product that simplified the kinetics. So he found first order decomposition of the methyl hydride, which means independent of the acetylene, of the alkyne, I should say. I'm just looking at my clock here. So I think I'm going to stop there, but or at least with that section. Again, we've got same story. Platinum hydrogen bond breaking is involved in the rate determining step. Okay, so he found that the formation of the CH bond involves breaking the metal hydrogen bond and the metal carbon bond. So let's just talk about this instead of doing the history lesson here. You know, people were very interested in how this kind of chemistry worked. And around that time, Bill Goddard developed a computational study. This is early computational study of transition metal chemistry. Now it's really commonplace, but this is back in 1980. 1986, computers were, you know, I didn't have a computer at home in that year. This was like the beginning of computer science. And these guys are computing the barriers to reactions. They used a very stripped down approximation of this. Actually, they did it for a bunch of different ones. I don't mean to just say that particular one. And they looked at the delta H double dagger. For making this metal zero complex and an RR prime bond. So they chose this to make the computations inexpensive. pH3 is very different than triphenylphosphine, you know, but they chose that ligand just to eliminate the number of connections that they had to compute, which makes the computations easier. And they did this for the platinum case and also the palladium case. And they looked at a series of different RRs. So they looked at hydrogen, they looked at methane, and they looked at ethane. Oops. And they computed the delta H of the reaction, the free energy of the conversion, and they also computed the barrier height. So for hydrogen, they found that this reaction was actually uphill, not favorable to make H2. The H2 would rather be stuck to the platinum center as two hydrides. And they found the barrier height of 14 kcals per mole. When they swapped out a methyl for a hydrogen and to make methane, now they found it was downhill. So the platinum methyl bond is not quite as good as the platinum hydrogen bond. Barrier height is a little bit larger. And then finally, it's 11 kcals per mole downhill to make ethane with a substantially higher barrier of 41. They did the same thing for palladium. Now it's really downhill. Minus 25, minus 42, minus 46. They found no barrier. And this one had a barrier of 10. Experimentally, bisphosphine complexes of palladium dimethyl decompose at 60 degrees C. Bisphosphine methyl palladium is not very stable. The platinum compounds are much more stable. Bisphosphine platinum dimethyl is, it's not a rock, but it hangs around. So why are the relative trends here? Okay. Palladium versus platinum, you're talking about difference in oxidation state preference. So platinum tends to make stronger bonds. It prefers higher oxidation states. This is a reductive process. You're making metal 0 from metal 2+. So platinum is less likely want to do that than palladium. And that's why for palladium, the delta H is substantially more downhill. Now, making dihydrogen versus ethane or methane, there's a consistent increase in the delta H double dagger for both metals. And the question is, why would that be? So the delta H double dagger for hydrogen to ethane largely has to do with the fact that a hydride is spherically symmetric. Versus a methyl, which kind of has an orientation about it. You gotta twist the orbital over. You know, to make that CC bond, you gotta break those metal carbon bonds. You gotta rotate things around, and so the more p orbital character in the bond, the harder it is to do that. The more s orbital character, the easier it is to do that. Okay, the transition state is the most bonding in the case of the hydride ligands. The CH is less bonding. So there's not a lot of reorganization that has to happen. This also applies for, say, phenyl or acetyl versus, say, methyl. As you go towards sp2 and sp, you get more s orbital character in the bond, and it becomes more amenable to reorienting. So reductive elimination and oxidative addition track with s orbital character. They get easier the more s orbital character there is. Okay, so I think I'm going to stop there. I wanted to just take a moment and say, I hope that you will fill out the course evaluation. I'm not actually plugged into what's going on there. I believe you've received something, and you know, your comments are going to be public and all of that stuff. I really would like you guys to give feedback on the class. It's an awkward year, obviously, but you know, I do really enjoy teaching the class, and I want to do a good job of it. And I think it's important that you give me some feedback. So I would appreciate it if you take the time to fill out those forms. You know, if you liked the class, I would appreciate it if you'd fill out those forms. You know, either just constructive feedback, thoughtful things that are going to help me and help people understand what the class is about. You know, I think it's a big service, honestly, to do that, and it's rare. I mean, I personally always like feedback, even when it's difficult. It's really important that you offer it. It's certainly welcome. And I appreciate you being patient with me. You know, getting things available to you on time, and errors and stuff like that. Yeah, it's been a little bit awkward, but I hope satisfying. You know, any direct feedback also, if you'd rather just sort of talk to me or send me a note about how to do better next time, or your thoughts about the class, I'd appreciate that kind of thing. It can be a little difficult to balance the content in a way that's appropriate for both the undergraduates and the graduate students. So if you feel like that part of the class is not wasn't well suited to you, you know, it's okay to say something along those lines. I'd like to hear that type of feedback. Yeah, otherwise, thanks so much for showing up and participating. And I will plan to see you on Monday, and I'll send you a link and clarify the time and all of that stuff. As I said at the beginning, the homework 6 can be turned in tomorrow at class time. Because of some of the errors we saw in the previous problem set, just to make sure that you guys are clear on how that electron counting is supposed to work. If you have any more questions about that need clarifying, I'd appreciate it if you post them on Piazza so that everybody can get a look at my response. And other than that, I will look forward to seeing you on Monday.
Thank you, Professor.
Thank you, Professor.
Yeah.
Thank you.
Thank you, Professor.